Hi everybody, this is Mrs. Yenny, and I'm going to complete the 1.3 multiplication, playing the multiplication game review. So in this game, remember you had to roll 2 number cubes or dice, multiply the numbers that came up, and record whether the product was odd or even. So in this example, I rolled 2 number cubes, 5 and a 4. 5 times 4 is 20, so I would record the product of 20 and then write that it was even. And after playing 36 times, as you can see I did here, I found that I had 7 of my products were odd. That's only 7 out of 36. And I found that 29 of my products out of 36 were even. So now I'm going to use this information to look at my experimental probability, and then I'm going to analyze the game a little bit further to find the theoretical probability, and of course to decide whether the game is fair. Alrighty, so let's get to that. Just like I said, 7 out of 36 I found were odd, 29 out of 36 I found were even. These are all the products. 7 out of 36 is approximately 19% and 81% for even. So it sure seems like this game isn't fair. In the beginning, I forgot to mention that player A gets 1 point if the product is odd, and player B gets 1 point if the product is even. So the points are the same, but our probabilities seem way off, so it makes me think that this game is probably not fair, but we're going to figure that out as we go through the theoretical probability. Alright, so first of all, to list all the possible outcomes, we could make a tree, but instead of making a tree, since I think that's probably how a lot of you are going to do that, I'm going to make an area model as a review of the Investigation 2 video that you watched. So what I'm going to do is I'm going to divide this area model into 6 parts vertically here to represent the 6 equally likely numbers that I could roll when I roll just 1 number cube. And now what I'm going to do is I'm going to separate the area model into 6 equally likely parts this direction to represent the 6 equally likely numbers that would result if I roll the second die. So now what I'm going to do is in each of these little cells, that's what I'm going to call them, I'm going to put the product of the numbers when I combine them. So for example, 1 times 1 is 1, 2 times 1 is 2, 3 times 1 is 3, and so on. 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. You get the idea. Here 1 times 3 is 3, 2 times 3 is 6, and so on. 1 times 4 is 4, 4 times 2 is 8. 4 times 3 is 12, and you get the idea. We'll go through the 5s now. 1 times 5, 2 times 5, 3 times 5, 4 times 5, and the 6s. Okay, so I can see I have 36 cells here, so first of all I'm just going to write down that I have 36 possible outcomes, and that's going to be an important thing to remember and to understand. In order to really analyze the theoretical probability, you have to know that 36 outcomes. I just want to show you really quickly what it might look like if you were to make a tree diagram to get all your possible outcomes. You would have to have 6 branches right off the beginning to represent the roll of die number 1, and of course you would label those all with the numbers on each of the 6 faces. And then off of each of these branches, 1, 2, 3, 4, 5, you're going to need another 6 to represent the 6 equally likely outcomes on your other die. So you can imagine that this is going to get pretty messy. But you would do that, of course, off of each of these branches. Okay, and I'm not going to complete it all since I have my 36 outcomes here. I think that'll be all right. Alright, the next one is each product equally likely. Well, this is a key word here, is each product equally likely. Because we would say that each individual outcome here is equally likely. But each product is not equally likely. And the reason I say that is because if you look at 4, for example, I can get a 4 for a product when I multiply 1 times 4, or when I multiply 2 times 2, or when I multiply 4 times 1. In any case, you can see that there are 3 different ways of getting a product of 4. But then look at 36. There's only one way to get 36. So the probability, this is my explanation here, the probability of a 4 is 3 out of 36. But the probability of 36, or say 25, or 16, for example, is just 1 out of 36. All right, so let's go to the theoretical probability. The theoretical probability of an odd. So what I'm going to have to do is count how many odds out of 36 I have. And I think I'll use my yellow here. I'm just going to put a dot in each of my odd products, 1, 3, and 5. And then look what happens here. All of these are even. Anytime I'm multiplying by an even number, I'm realizing that an even times an even gives me an even. But I also notice that an even times an odd also gives me an even. And the other thing I notice is that an odd times an even also gives me an even. So look at that, shows up here because all of these numbers here are even. So we're not going to count those. All of these numbers here are even. So we're not going to count those. All of these numbers here, these products, are even. So we're not going to count those. Same is going to be true for all in this column, multiplying by that even number, multiplying by that even number, multiplying by that even number. So now if you look at our grid, you can see that we're just left with simply 9 out of 36, which reduces, of course, to 1/4, or about 25%. And then the probability of an even, all the ones that I ended up coloring yellow, I guess, so ignore those yellow dots, are what's left from 36 when we take away our 9, and that's 27 out of 36, which equals 3/4, or 75%. Okay, suppose the game had 100 rolls rather than 36. How many points would you expect each player to get? Well, I want you to think about what percent means, because we have turned all of our probabilities into percents. And what that means is 25%, remember folks, means 25 out of 100. 75% means 75 out of 100. So how many rolls, how many points would we get if we played 100 times? Well, I would expect an odd player to get 25 points out of 100. I would expect an even player to get 75 points out of 100. So lastly, is this game fair? Well, no, it's not fair. It's not fair because look at this. Out of 100, you would expect player A to get just 25 points and player B to get 75 points. That sure doesn't seem even. And we know that because look at our theoretical probabilities. They're way off. And one of the things that makes a game fair is that your probabilities match up. So before we talked about how the points were the same, but our probabilities are off. So now what we need to do is we need to adjust our point values in order to compensate for that difference in our probabilities. So for example, we're going to take the 1/4 and compare that to our 3/4. Probability of an odd product, probability of an even product. Well, if I take my probability of an odd product and I give that player, player A, 3 points, look what happens. And then if I leave my probability for an even product, or my point values for an even product at 1, then look what happens. Now I have a fair game. All right, I hope that makes sense to everybody. If you have further questions, make sure that you ask them. See me in class, and thanks for listening.